All right. Good morning. I hope you're all doing well. It is Wednesday, April 15th. It is snowy outside. I hope you all are toasty and warm. I've got my blanket back here in case it gets a little chilly. But want to just jump right in and introduce our next topic, which is on what we call waves and superposition. So first thing we're going to do is I just want to briefly go over the homework, and then we'll jump into the new topic. So let's switch the camera here. So this was the homework that is due today, and there were a couple things people pointed out that were missing, and hopefully you guys caught this. The first one was missing and the first problem was the speed, and all radio waves travel at the speed of light. That was something that I forgot to share with you guys in the last problem. So the speed of light, and I fixed it here, the speed of light is 3 times 10 to the 8th meters per second. It's ridiculously fast. 3 times 10 to the 8th, so that's 3 with 8 zeros at the end of it, meters every second. And so this problem says radio station WCRB in Boston broadcasts at a frequency of 99.5 megahertz. What is the wavelength of the radio waves emitted by WCRB? So let's start here. We're going to list the variables. So we know that the frequency, F, is equal to 99.5. And the M means megahertz. So mega is times 10 to the 6th hertz. And we want to know what is the wavelength, and lambda equals question mark. And this was the one thing that was missing before, but the velocity of the wave is given by this letter. C is the constant that we use in physics to represent the speed of light. It is 3 times 10 to the 8th meters per second. So the next part here is we're going to write out an equation. We know that V equals lambda times F. And we want to rearrange this to solve for lambda. So I'm going to divide both sides by F. Divide by F. All right, those cancel out. And so I get lambda equals V over F. We're going to solve this problem here. So lambda equals 3 times 10 to the 8th meters per second divided by the frequency, which is 99.5 times 10 to the 6th hertz. And then we plug this into our calculator. So let's get the calculator out here. So 3 times 10 to the 8th divided by 99 times 10. 99.5 times 10 to the 6th. And you get 3.01. And we see that this is 1 over seconds. This is also hertz, which is 1 over seconds. Those cancel out, and we're left with units of meters, 3.015 meters. All right, let's do a couple more here, and hopefully these are all pretty straightforward. So number 2 says, in California, Clay is surfing on a wave that propels him towards the beach with a speed of 5 meters per second. And the wave crests are each 20 meters apart, 20 meters apart. A, what is the frequency of the water wave? And B, what is the period? So let's list our variables. So we know that the velocity, move this so that I'm not in my head, velocity equals 5.0 meters per second. The next one is that we know that the crests of the waves are 20 meters apart, so that tells us what the wavelength is. Lambda, wavelength, is equal to 20 meters. And we put that dot there to show the sig figs that's a significant digit, the 0 there. And we want to know what is the frequency. Right, so F equals question mark. So again, we say V equals lambda F. In this case, I want to solve for F, so divide both sides by lambda. Divide by lambda, let's cancel out, and I get F is equal to V over lambda. We solve this by plugging in the numbers. F equals 5.0 meters per second divided by 20 meters. Again, here we can see that the meters and the meters cancel out, and we're left with 5 divided by 20. This is 1/4, so 0.25 hertz. And then the second part is, what is the period? And so we know that t is equal to 1 divided by f. And so 1 divided by 0.25 hertz gives us, and this one we can do without should be able to do without a calculator, right? 0 divided by 1/4 is equal to 4.0 seconds, right? Good. Let's take a look at one more here. Let's see. Let's take a look at number 5. All right, so number 5 says, while flying to Tucson, Connie's plane experiences turbulence that causes coffee in her cup to oscillate back and forth 4 times each second. The waves of the coffee have a wavelength of 0.1 meters. What is the speed of the wave moving through the coffee? So it says that it's going back and forth 4 times each second. So each second, this tells me what the frequency is. So this is cycles per second, so 4 times per second. So we know that F is equal to 4 hertz. We know that the wavelength, lambda, is equal to 0.1 meters. And we want to know how fast is the wave moving, right? So how fast is that wave actually moving across the coffee cup? So the equation is V equals lambda times F. We don't have to do anything to rearrange this, so it's the same equation. Draw an arrow there. I'm going to solve it now. V is equal to lambda, which is 0.1 meters, times 4 hertz. And we work that out. 0.1 times 4, I don't even need a calculator for this one, is 0.4 meters per second. Right, so these answers were given to you guys here. So hopefully that helps. And if you have questions as you're finishing this up today, send me an email, and I can work out a couple more of these. So hopefully that is helpful. So let's go back to these slides. So now today I'm going to talk a little bit about waves and what happens when waves collide or interfere with each other. So before we do that, I want to talk about what happens when just regular particles collide. So we talked about this last semester when we had the carts bumping into each other. And in what we consider classical mechanics, when two things collide, they can do one of two things. They either bounce off each other, which is what we call an elastic collision, or they stick together and move. But what we know is that they cannot occupy the same space at the same time. That's what we call classical mechanics, right? So I've got a couple of plastic things here, right? So two cats, right? So when one cat moves and the other cat hits the other cat, right? They can't occupy the same space, right? So they either hit and bounce or they hit and stick, but they can't occupy the same space. That's what we call classical mechanics. In wave mechanics, some interesting things happen. So here, we're going to watch the wave hit the end here, and it's bouncing back, but then it passes almost seemingly right through the wave. And so waves have a very unique characteristic in that they can actually occupy the same space, and that energy, the energy of the wave, superimpose on top of each other. So this is what we call superposition, where they basically overlap on top of each other. So here, let's watch this animation again here and see what happens. So I want you to watch. So at the very beginning here, so here we go. So here at the very beginning, one wave starts out. It's going to move over to the right. It's going to bounce back, and it keeps moving and passes right through. Notice that they added together when they passed there. And then this one also seems to keep going and bouncing, passing right through. So this is what we call superposition. And before we dive too deep into superposition, I want to just briefly talk about what happens when waves interfere or interact with a boundary condition. So boundaries are defined anytime the conditions change. So a condition can be the material it's traveling through, the material itself, or just an object that's in the way. So there are four main interactions that happen with waves. These are reflection, refraction, diffraction, and absorption. And we'll go into more detail on these later, but what I want for your notes to write down are, the first is the easiest, which is reflection. So when a wave hits a boundary, like a wall, it simply reflects off, it bounces off. And this is easy for us to understand in terms of classical mechanics, right? It's like if I were to take a tennis ball and throw it against the wall, it would bounce off at the exact same angle it hits. And so that's what we call reflection. And this happens anytime there's a boundary condition. So if I had, for example, two ropes tied together, one that's heavy and one that's thinner, and I were to create a wave on the thin rope and it hits the thick rope, there will be a reflection that happens when there's that boundary. The second thing is what we call refraction, and I just noticed that my camera is covering up half of the slide, so let me move this way. So refraction happens when waves pass through a boundary, so from one material through into another material, and what happens is when it goes from one material to another material, the speed of the wave changes. That was something we talked about in our last lecture, was that the speed of the wave is determined on the material. So thicker, heavier materials, sound has a different property and travels at a different speed. So in fact, speed travels faster in things like water than it does in air because the molecules are closer together, right? Imagine that they're just bouncing off each other, and so you can get sound to travel faster in more dense materials. So here is an example of refraction. This is any of you guys who wear glasses or wear contact lenses. This is how lenses work. Here we have a wave that's traveling through, we assume, air. And when the wave hits the glass or the plastic here, the speed of the wave changes. And what ends up happening is that also then bends the wave and causes what we call refraction. The third one is kind of a unique one, and this one is a little puzzling. This one is one of the phenomena that really puzzled early scientists, and it's what we call diffraction. So when waves hit an edge, so like the edge here, this edge, it doesn't just kind of bounce off. In fact, what happens at the edge is that the wave will bend around it, and is what we call diffraction. And so something that's fun to do if you ever go outside on a day that's sunny, and you put your hand up and you look at the shadow that's cast on the ground, you'll see that there's actually usually two shadows. There's what we call the dark main shadow, and then there's a sub-shadow behind it. And that's because light is in fact bending around the boundary condition, the boundary of your hand, passing around. And they have names for them. I forget the names. I think one of them is penumbra, and then the other one is, I don't know. You can look it up. But that's what we call diffraction. So, and it's really an interesting phenomenon. We'll talk more about that in a future unit. And then the last one is absorption. So this is basically when a wave travels from one material into another lossy material, and some of that energy is absorbed, and so kind of dissipates. So those are the four main things: reflection, refraction, diffraction. Oh, I can just move out of the screen. And absorption, right? So those are the four main things. So let's look at what happens here. And in this case here, we have two different boundary conditions shown here with a wave on a string. So notice on the top example here, we have what we call a fixed end. And when the wave hits the fixed end, it gets reflected back, but the wave also is inverted. So here the wave starts on the top, hits the end, and then reflects back on the bottom. And so that's what we call a fixed end boundary. The other option is what we call a loose end boundary. And here in the simulation, we've got a little ring that's sliding on a pole, so it can slide up and down. It's still a boundary. And so when it hits that end, let's watch it here. It goes all the way over to the right. It slides up, and the wave reflects back, but on the same side. And so these two conditions can create some interesting phenomenon that we're going to study when we talk about things like sounds. So let's look at this simulation here again and watch what happens. And actually, I'm just going to open up the PhET link and see if we can show this. So let's see. Oops. So in the PhET link here, if I create a pulse here, I'm going to turn off damping. I'm going to restart this. So now we have this wave. And because I've turned off damping, this wave is going to reflect back and forth forever. One of the things I want you to notice here is that the wave, this wave that's moving back and forth, is going from left to right and back. But the particles in the string are only moving up and down. So if we were to focus on, say, this green particle here, the green particle gets pushed down, then gets pushed up, gets pushed down, gets pushed up, right? That green bead is not actually moving from left to right. It's only moving up and down. And so this is what we call a transverse wave. So now I'm going to put another wave here, and it looks like they're switching positions, but in fact they're not switching positions. Here, let me restart this because I'm going to shorten that pulse width so we can see. So there's a little tighter wave. All right, so we've got one traveling back and forth. I'm going to send another one. And so here I'm going to slow this down. How do I slow this down? Slow it down. Right, so here we've got the two waves, and this wave, in fact, just keeps moving and it passes right through it. So this wave on the top passes right through it. But notice what happens when they're directly on top of each other is that they superimpose and they cancel each other out. This is what we would call a destructive interference. The other option that happens when we have a loose end here, let's restart this. So on a loose end, so there's one wave hitting, another one, and this is going to bounce back on the same side. Now when they're on the same side, notice they add together and they create a larger wave. So these are some concepts we call superposition. Edit, 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 edit. All right. So here's another slide just to illustrate this idea of what we call superposition. And there are two kind of categories that are oftentimes described. One is called constructive interference, and then the other one is destructive interference. So constructive interference here is when we have the two waves that are both on the same side, and they add together, and they constructively interfere. So they construct to make a bigger wave. But after they collide, the two waves continue moving, right? They continue moving, almost as if they are separate things. They are separate things, right? So this wave on the right is moving to the left and continues moving to the left, right? Is moving to the left here. It's still moving, right? But at this snapshot in time, they are exactly on top of each other. And then sometime later, this wave continues to move back to the left, and then the other wave is moving to the right. The second topic, or the second category, is what we call destructive interference. Destructive interference is when the two waves are opposite of each other. One's on the top, one's on the bottom, and they pass through each other. And when they overlap exactly, they cancel out. And so you see that here in this image. So the last thing that you will see times is funny waves, right? So and this property can be used with, so we do it with simple examples of little bumps and hoops and things like this, just because they're graphically easy for us to represent. But you can do this with any number of waves. So superposition principle works for not just 2, not just 3, but any number of waves. And so if we have, say, wave A, a high frequency kind of squiggle, and then wave B, which is a lower frequency wave, right? So lower frequency wave. And we were to put them both on the same string, you end up superimposing the high frequency on top of this low frequency. And we, in radio communications, we call this a carrier. So this is some of the ways that we use to communicate or send communications over radio signals. But basically, what superposition is simply addition, right? So A plus B is equal to C. So let's take a look at some problems that you guys will be doing for homework today. So this is the superposition wave problems. So let's see if... So these are been PDF'd for you guys and are going to be posted on Classroom. So on the left-hand side is basically an example of superposition of two waves. So we'll just read this together here. A pair of pulses travel towards each other at equal speeds. The composite waveforms, that means the addition of the two waveforms as they pass through each other and interfere, are shown in 1-second intervals. In the left column, note how the pulses interfere produce composite waveform, the solid line. So now we're going to make a similar construction of the two wave pulses on the right column. So let's just review what's going on here. So this one is moving to the right, this one's moving to the left, right? Still moving to the right, still moving to the left, right? And they're moving basically 1 dot per second, right? So here they're another dot closer, right? Still moving. Here they're overlapping, right? And so the dotted line shows roughly where they are. And basically what we're doing is we're just adding all of these waves together, right? And then in 4 seconds, they are exactly on top of each other. So this adds, so we've got 2 of these, they add up to there. We've got this, there are 2 of those, that adds to there. Here, we've got 2 of these, that adds to there, right? And so on and so forth. Now we've got, let's see, which one was the one? Let's go back here. At 2 seconds, we've got, I wish we could color code this. This one is moving to the right. Now this one is moving, oh, this one's still moving to the right. And this one's moving to the left, right? Now we've got one moving to the right, one moving to the left. This one now is moving to the right. This one's moving to the left. Oh, I mixed that up. Sorry. This one is going to the left, and then this one's going to the right. And now they're passing past each other, right? And they continue to move. All right, so now let's try this with these two. These two waves are now opposite of each other. So in the first example here, this is what we would call constructive interference. The second one, we would call it destructive interference. So 1 second later, this is going to be here. This is going to be here. Here. So this first wave is going to look like that. This wave is going to be oh, I didn't do that right. I'm sorry. sure I line that up, right? So that's 1 second later. 1 more second later, this one is going to be here. 2, 3. 1, 2, 3. And then this one is going to be here. 1. And they haven't started overlapping on top of each other yet, right? So there's still 2 separate waves. Now this at t equals 3 seconds, this is when they're going to start overlapping. So this is where, so this one is going to go here. 1, 2, 3. So that one goes there, that one goes there. And then this other one, let's see, was here, right? So it's going to go over 1 second. 1. So now we had to figure out how are these going to overlap on top of each other. So here, I've got, this is 0, that's 1. Sorry, 2 dots up, so that's going to be the same. This is 1 up here, 1 down, so that's going to be a 0. So what I see here is this is going to be there. I'm going to try to make this dark here to show what's happening. Right. So you see what ends up happening is these 2 cancel out right here in the middle to make it 0. 1 more second later, so now this one's going to be here. And then this one is going to be here. And so now what's going to happen when you've got them directly on top of each other? They're going to cancel out, right? And I probably shouldn't have done this in pen, as I'm just realizing that. This third one is going to look, I think, similar to this one, except for it's going to be flip-flopped, right? So this bottom wave is still going to the left. So here, I want to put this one here, 2, 3. So I'm going to do a dotted line. That's that one there. This one is a dotted line here. All right. That's what I should have done with the dotted line. So those don't interfere with anything. So that's solid line, solid line. And then here, I've got 1 on the top, plus this one is at 0. That's going to add to just this. Here I've got 1, positive 1. Here I've got -1. Those are going to cancel out to be 0. And so here, well, that was a much better way of doing it. Right. And then the last few, you guys can finish. So that's an example of what this might look like. So for your practice, you guys will do the same example here with these 2 waves in 1 second intervals. So assume that it moves 1 dot each second. And so this wave, the left wave, is moving to the right wave is moving to the left. And so you'll do that for 8 seconds, so all the way down on here. And then on the second page is a few more examples. And here I'm going to have you show just 3 snapshots. So this is what we call snapshots in time. For each of these, we can assume that's moving at 1 meter per second. So 1 second later, this kind of square wave will be 1 meter farther over to the right. This one will be 1 meter farther to the left. Right? So you'll do it at 1 second, 1.5 seconds, and 2 seconds. If you have a printer, you can print this out, and on the last page is a little grid. If you don't have a printer, you can just sketch this out on loose leaf paper. These shapes are pretty straightforward and easy to do. So hopefully that's helpful, and if you get stuck on any of this, send me an email, let me know, and I would be happy to help. So we'll come back to standing waves again on Monday. So Friday we won't have class. Enjoy the day off, and but if you have questions, let me know. I hope you all are doing well, and that's a wrap. Bye.